Okay, so this section is talking all about related rates, which means we're going to have to do a lot of implicit differentiation, okay? So taking derivatives with respect to specifically time in this case, because I'm looking at, like, if I kind of explained this to you guys a little bit last class. Like, can I borrow this really quick? Yeah. If I'm filling this bottle of water, what is the rate at which it is filling? So if I'm looking at this bottle of water, I'm looking at specifically volume. Okay, how is the rate of volume changing as I pour water in, right? As I pour water in on the bottom, it's going to be going in a little bit slower than if it goes in right here where it's a little bit thinner. Does that make sense? So we're looking at the rate at what things are growing. You'll either be looking at volume, you'll be looking at area. So your units need to make sense and match your answer. Okay, so if we have something in area, that means we should probably have something like, feet squared per second. If we have something in volume, that should be something probably like feet cubed per second or something like that. Okay, so make sure your units match up with what your answer is. But basically, if you see these words of increasing, decreasing, growing, or shrinking, those are usually good kind of, what is the word I'm looking for? Like buzzwords of meaning we're going to have to find a related rate and we're going to have to solve it using implicit differentiation. Okay. So change occurs over time. So when we're talking about how a quantity is changing, we're going to be talking about the derivative of that quantity with respect to time. Okay, so we're going to get an example of just doing a quick 4 of these, writing a statement mathematically with a rate and a time. Okay, so if I said, okay, let's write the following as a math statement. John is growing at the rate of 3 inches per year. That means his height is changing, right? So his height is changing 3 inches per year. So if I wanted to write that out, I would say something like dH dt is equal to 3 inches per year. I would get in the habit of writing the notes, or writing the units with it. So that way at the end, when you're trying to figure out what the units of your rate is, you'll be able to figure it out a little bit quicker, okay? I'm going to go down to letter C before I jump over to B. The radius of a circle is increasing by 4 feet per hour. What do we want to choose for radius for our unit? R. So the radius is changing with relation to time. So dr dt is equal to 4 feet per hour. Okay, both of those were increasing or growing. Letter B says my mutual fund is shrinking by 4 cents per day. So what do we want to choose for mutual fund? What letter? M. Okay, we could have chose M, we could have chose F. It doesn't really matter. But our mutual fund relation with time is shrinking. So that means we're going to have a negative in front of that 4. So negative 4 cents per day. Now, units are really important. Is it negative $4? Is it negative $4,000? Is it negative 4 cents? Negative 4 cents is a lot less bad than negative $4 or whatever. Okay, so make sure you got your units there with it. Volume of a cone is decreasing by 2 inches cubed per second. So the rate at which the volume is changing is 2 inches cubed per second. It's getting smaller. So what variable do you want to use for volume? V. So dV dt is equal to 2 inches cubed per second. Thank you. It is negative. Yes. Good catch. Okay, so we're going to have to write these kind of statements for different pictures that we're given. We're going to start out with just some 2D shapes, okay? And then we're going to work our way up into some 3D shapes. Now, in this unit, if you don't know the formulas for things, it almost always is given to you, but if it's not, and if it's on a quiz or a test, just ask me for the formula. If you don't know what the formula of like a cylinder is off the top of your head, that's fair. It's been a minute since we've done that, okay? Just ask and I will give that to you. Sound good? Cool. All right. So first example here, I've got a rectangle. Okay, this rectangle is undergoing changes to its length and its width. So basically think about a rectangle and things are happening. I'm either going to be stretching it, I'm going to be shrinking it, or maybe one of them is getting bigger, but then like one of them is getting smaller. Okay, so like something is happening with my rectangle and it's going to tell us about it right here. Okay, it says, letter A, its length is increasing at the rate of 2 inches per second. Its width is increasing at a rate of 3 inches per second. Find out how fast my perimeter is changing the moment the length is 10 and the width is 6. That was a lot of information. Always, always, always draw yourself a picture to start out. Okay, so I'm going to draw myself a picture over here on the right. What'd you say?
Do we know what type of rectangle it's starting at?
We do, yes. It says its length is 10. So let's go ahead and say my length and my width.
Yeah, but at the moment, it's the perimeter's length is 10.
Oh, I see what you mean. Yes. So no, we don't. But you're going to find out that it's actually not going to matter. I'll show you what I mean. So my given stuff, I'm going to kind of just draw on my picture, or feel free to write it out as well. It doesn't matter. But my length here is 10 inches. My width is 6 inches. That's the specific time we're looking at when the rate of the length is 2 inches per second and the width is 3 inches per second. So I'm going to write that. I kind of ran out of space here. So we'll do dl dt is at 2 inches per second, and dw dt is at 3 inches per second. So we're finding the perimeter. So who knows the formula for the perimeter of a rectangle? 2L plus 2W, right? So our formula we're going to use is P is equal to 2L plus 2W. And we are finding when the perimeter is changing. So we're finding the rate at the perimeter changing. So that means I'm finding dP dt. We're finding this specifically when your length is 10 and when your W is 6. We're finding what is the rate at those two specific times, or that one specific time, when you have a length of 10 and a width of 6. Okay, so we have some information here. We know what dl dt is, we know what dw dt is, but we're not going to plug those into our formula right away because do I have a dl or a dw here? No, how are we going to get one of those things? By taking the derivative. We have to take the derivative with respect to time before you plug in the information that you know. Okay? So after we've drawn our picture, after we've written down what equation we're going to use, we are now going to take the derivative. So the derivative with respect to time of P equals 2L plus 2W would be dP dt is equal to, this is where that implicit differentiation comes into play. I've got 2 times, what's the derivative of L with respect to time? How do I write that?
Just
dl dt. Okay, then I've got plus 2 times the derivative of W, so that would be dw dt. Anyone ever watch Arthur as a kid?
Yeah.
DW?
Yeah. That's what I was thinking when you said
I know. Someone last class was drawing a picture, or like inserted a picture of DW in there as well. Yeah, good times. Okay, so now I can actually plug in some information that we know, right? dl dt is equal to 2 inches per second, right? So I'm going to plug in that information here. And then I'm also going to plug in the information of dw dt is equal to 3 inches per second. Okay? When I'm plugging it in, I'm also plugging in the units. So I've got dP dt is equal to 2 times 2 inches per second plus 2 times 3 inches per second. Now, what is my units on the right-hand side going to be if I add those together? Inches per second, right? And it should be a rate because we're looking at the rate at which the perimeter is changing. So if I simplify the right-hand side, 2 times 2 plus 2 times 3, that's going to give me what? 10. So I've got dP dt is equal to 10 inches per second, and that is it. Since I'm just adding, I'm not multiplying, so my units aren't becoming inches squared, seconds squared. It's just 10 inches per second squared. Okay, but what does that actually mean? What did we actually just find? Okay, we just found, it says how fast the perimeter is changing. So the perimeter is changing at a rate of 10 inches per second. It's specifically increasing at that rate. Okay, so I want to write down what that kind of means. You don't have to write this out every single time, but just so that you know what this dp dt stands for, I'm going to write this out here. So I've got the perimeter of the rectangle is increasing at a rate of 10 inches per second. Keywords being increasing and rate, okay? And then obviously also the units. Can't forget the units. Make sure the units make sense in terms of the problem. If we're looking at how our perimeter is changing at a rate, okay, it's changing at a rate of 10 inches per second in this case. Okay. All right, letter B is still going to use that same picture from up above, except for the only thing that's changing is our rate of our length and our rate of our width. Okay, it still has the length of 10 and the width of 6. That's the specific moment we're looking at. But its length is increasing now at a rate of 3 inches per second. So I would write that as dl dt is equal to 3 inches per second. And my width is decreasing now by 2 inches per second. So it's going to be dw dt is equal to negative 2 inches per second. But am I still using my perimeter formula? What is it asking us to find here? How fast the area is changing. How do I find the area of a rectangle? Length times width, right? So my equation that you're going to use is area equals length times width. And we are solving for, we are finding dA dt. We're finding dA dt specifically when the length is 10 and the width is 6. And before I can actually plug anything in, we have to take the derivative, okay? So I'm taking the derivative of A equals L times W, which means I'm going to have to use the product rule, okay? So derivative of A, that's just dA dt. Okay, then depending on how you do your product rule, your answer might look a little different than what I'm going to write down, but you should have the same thing split up with addition symbols, okay? So I'm going to leave the first one times the derivative of the second one, so times dw dt. And then I'm going to add that with, I'm going to leave the second one alone and times it by the derivative of the first one. You could have had the order of those flip-flopped, but you should have those 4 things when you're taking the derivative of a product. Okay. Well, now, don't I know all this information? Yeah, so I can just plug all of this information in, right? So my dw dt is going to be negative 2. Your dl dt is that positive 3. And then I've got 10 and 6 for my length and my width. Okay, so let's plug all that information in. So dA dt is equal to 10 inches, always use those units, times negative 2 inches per second, plus my width, which is 6 inches, times dl dt, which was 3 inches per second. Now, if we think about what makes sense in terms of my answer, if I'm finding how fast area is changing, area as just units by itself should be something squared, right? But if it's a rate, I'm looking at units squared per something time. So per second, per minute, per hour, something like that, okay? Am I going to get that there on the right-hand side? My units here? What are my units going to be?
Inches squared per second.
Inches squared per second, right? So we're good. And they're both inches squared per second. If somehow when you plug in your values for your derivatives, if these two things don't match up when you're adding them together, that means probably you did something wrong somewhere. Maybe you took the derivative incorrectly, okay? But I can go ahead and simplify this. So my derivative of my area with respect to time is going to equal 10 times negative 2 plus 6 times 3, which is negative 2 inches squared per second. Okay, so if I was going to explain what this actually means in terms of the problem, using that kind of same setup that I did up there in red, we're looking at the area of a rectangle is decreasing at a rate of 2 inches squared per second, okay? Make sure if you're saying decreasing, you don't also say it's decreasing by negative 2, because then it kind of like contradicts each other, or contradicts, that's the word, contradicts each other, okay? So make sure you're using the decreasing or increasing words by the symbol in front and then telling me what the rate is, okay? Questions on these two? All right, moving on, we're talking about now some triangles. When I say triangles, what flashbacks from geometry come back to you?
1/2 base.
1/2 base times height. That's your area formula, right? What else comes back to you?
Sine, cosine, tangent.
Sine, cosine, tangent. And wait, someone said it back there, I think. Pythagorean theorem. Yes. Okay, all three of those things are going to be things that we're going to use. And then we're also going to apply some calculus to it. Okay? But the first thing that we need to know is how to actually find those formulas. So if you don't know those formulas, please ask or look them up on your homework if you don't know what the formulas are, okay? So I've got a right triangle whose side lengths are changing. The short side is increasing and the long side is decreasing. And then we're given those two rates. Okay, when they say the short side and the long side, they don't mean the hypotenuse. They mean like the legs of the triangle itself, not the hypotenuse, okay? So let's go ahead and draw ourselves a picture here of our triangle. That was a terrible triangle. This is why Notability is so much better.
I remember when I used to have to prove that these things were real.
So I'm going to label this my short side with S and my long side with L. Okay? So we are given some things. We are given that the short side is increasing at 3 inches per second. So I would write that as ds dt is equal to 3 inches per second. Then my long side is decreasing. So how would I write my long side decreasing at 5 inches per second? The other what? Yeah, -5, right? dl dt is equal to -5 inches per second. And we're looking at finding the rate of change of the area. So area formula. What is my area formula for a triangle? 1/2 base times height. Now in this case, I'm going to use the variables that I chose. Okay, my variables that I chose were L and S. So I'm going to do 1/2 L times S. And we are specifically finding the rate of change of the area, so dA dt, when my short side is 30 inches and my long side was 40 inches. Okay, I'm not plugging those values in right away until after I take the derivative. Okay, so I need to take the derivative of A with respect to t. So dA dt. How am I going to take the derivative of this? What am I going to have to use? Product rule, right? I've got 1/2 L times S. Okay, so I'm going to leave the first one, 1/2 L, times the derivative of the second one. Derivative of S would be ds dt. Then I'm going to add that with I'm going to leave the second one alone. Times it by the derivative of 1/2 L. What's the derivative of 1/2 L? 1/2 times dl dt. Okay, your order of those things could be switched, but did we all get that derivative? Okay, and now that I've taken the derivative from here, I can go ahead and plug everything that I know. I know that my ds dt is equal to 3 inches per second, and I know dl dt is negative 5 inches per second, and then I know what s is and what L is equal to. So let's plug all that information in. I've got dA dt is equal to 1/2 times 40 inches times 3 inches per second plus S, which was 30, if I remember right. Yep, 30 inches times 1/2 times dl dt, which is negative 5 inches per second. Now, before we actually go and simplify this on our calculator, what are my units going to end up being here on the right-hand side? Inches squared per second, right? These both are inches squared per second, which means we took our derivative probably correct, okay? If it didn't match, then that means I would go back and try and figure out where did I make a mistake when I was trying to take the derivative, okay? So now we're just going to plug all this stuff into our calculator. So dA dt is equal to, if I multiply all these things together and combine my like terms, take my word for it or plug it in and check, you get negative 15 inches squared per second. Okay, so what does this mean? Tell your neighbor, what does negative 15 inches squared per second mean? Kind of give me that confirmation statement there. All right. We got another triangle in here. It says, how fast is the hypotenuse changing at the moment? The short side is 30 and the long side is 40. So same length and width that we're looking at there, or not length and width, but same legs of our triangle, but we're looking at the hypotenuse now in this case. So I'm going to go ahead and I'm going to use the same picture from above. I'm just going to label this H. We're trying to find the hypotenuse rate. So what do you know? What formula do you know that relates all the sides of a triangle?
A squared plus B squared equals C.
A squared plus B squared equals C squared. In the terms of our equation, we're going to use
S squared plus L squared.
Yeah, L squared plus S squared is equal to H squared.
Or H equals square root of L squared plus S squared.
Yes, but I think taking the derivative of that might be a little bit gross. But, I mean, it should work either way. And so we are given the same information as up above. Okay, so we still know that my ds dt is equal to 3 inches per second. And I still know that dl dt is equal to negative 5 inches per second. Okay, so now this time we are finding the relation of our hypotenuse. How fast is our hypotenuse changing? So that's going to be dh dt when our side length is 30 and our length is 40. Okay, so before I plug in values, we have to take the derivative, okay? So I got to take the derivative of L squared plus S squared equals H squared. Go ahead and try taking the derivative with respect to time of your equation right there. Oops.
Is your answer a fraction? I love it.
Okay, so I'm going to take the derivative here, follow along, or keep on working if you are on the right track here. So I'm going to have 2L times dL dt plus 2S ds dt is equal to 2H ds, dH dt. Okay, once I have all those things, I can go ahead and plug in all the information that I know. Now, we're going to run across a problem here because do I know what my hypotenuse is?
We can figure that out.
No, but we can figure it out. How can we figure it out?
the Pythagorean.
Pythagorean theorem. And why is this one so nice? 3, 4, 5 triangle, right? If this here is 30 and this is 40, h has to be 50, either by using the Pythagorean theorem or knowing your Pythagorean triples, okay? So my height is 50. So I'm going to plug in all the information that I know into this formula here. So I've got 2 times 40 inches times negative 5 inches per second plus 2 times s, which is 30 inches, times ds dt, which is 3 inches per second. And all of that equals 2 times my hypotenuse. My hypotenuse was 50. We found that with the Pythagorean theorem. And then I don't know what dh dt is. Okay, that's what we're trying to find. So on the left-hand side, if I look at my units, I have inches times inches squared, or sorry, times inches per second, and then I have inches times inches per second. So my units on the left-hand side are what? Inches squared per second, right? So on our calculator, I would go ahead and plug in 2 times 40 times negative 5 plus 2 times 30 times 3. And if you plug all of that in, what do we get? Let's see.
Oh, negative 11. I realized what I did wrong. I forgot to square root it after I found the, like...
Hypotenuse.
Yeah.
So I got negative 220 inches squared per second is equal to 100 inches times dh dt. Now, if I'm trying to solve for dh dt, I got to get rid of that 100 inches. So now's where the units come into play, because if I divide by 100 inches, what is my units going to be? Inches per second, right? So that goes away. I'm left with dh dt is equal to, I can simplify this fraction to negative 22 over 10 inches per second. But I can simplify that one more time, right? So our dh dt is actually equal to negative 11 divided by 5 inches per second. Decimals are fine as long as, like, this next problem that we're going to do when we're talking about cylinders and when there's circles involved, there's obviously going to be a pi that's involved, right? So when there's a pi involved, I don't want you to give me a decimal answer. I want you to leave it in terms of pi. But if you're leaving your answer as a decimal in this case, that's fine, okay? All right, tell your neighbor really quick, what does this negative 11 over 5 inches per second mean in terms of the problem? Cylinders. The next example we're talking about are cylinders, specifically a right cylinder.
What does it even mean?
A right cylinder means basically it forms a right angle on the bottom. So if I were to draw a picture of this is probably going to be poorly done here on Explain Everything.
Do not all cylinders do that? No, apparently don't.
Let's see.
We're just making stuff up now.
Yeah, what is all?
Okay, so anyways, bringing it back together, we have a right cylinder here, okay, whose dimensions are changing. All right, so for this first example here, it says the radius is growing at 2 feet per minute. So I would say dr dt is equal to 2 feet per minute. The height of our cylinder is shrinking at 3 feet per minute, so that would be dh dt is equal to negative 3 feet per minute. Find the rate of change of the volume of the cylinder at the moment the height is 10 and the radius is 8. So our formula for volume of a cylinder, anyone know it?
2 pi r squared.
Not quite. If we're looking at area of a cylinder, we take the area of the base times it by the height. So close. Your area formula is pi r squared times h. Okay, that is your, not area, sorry, your volume. That is your volume formula.
Is the 2 the circumference? The 2 pi r squared means something. I don't know what it means.
All right, so here's our equation. We are trying to solve for the rate at which the volume is changing. So we're solving for what? dv dt. Okay, specifically when my height is 10 and when my radius is 8. I need to take the derivative of this equation before I start plugging anything in. So, dv dt.
2 pi.
dv dt. Now, I would suggest let's just leave pi out of this until the very end, okay? Because otherwise, it's going to get a little messy. You're going to want to try and multiply. Let's not multiply with the pi. We're going to leave the pi on the outside first. And then we're going to do the product rule with r squared and h, okay? So product rule with r squared and h. I'm going to take the derivative of r squared. So that's 2r times dr dt times h, right? The derivative of the first one times the second one, plus the derivative of h, which is, well, dh dt, right? And then times r squared. Again, your order of those things might be different depending on how you take the derivative using your product rule. Okay? So now, do we have all the information we need to solve for dv dt? Do we know our radius?
Yeah.
Do we know our height?
Yeah.
Do we know our dr dt
Yeah.
and our dh dt?
Yeah.
Yes, plug all that information in. So I've got dv dt is equal to, we'll leave pi out of this until the end, keeping all of my units involved. Oof, that was a lot of stuff.
Don't tell me.
Are my units on the left and the right side of these parentheses, or of this plus sign, going to match up?
No.
No?
Yes.
You sure? Yeah, I've got feet times feet times feet. That's feet cubed over minutes. I've got feet times feet squared over minutes. Feet cubed over minutes, right? So, and that should make sense, right? Because we're talking about volume. Volume should have units cubed in respect to time. So units cubed over time. And then if I plug in everything on the right-hand side of this equation into my calculator except for the pi, so plug in everything 2 times 8 times 2 times 10 plus negative 3 times 8 squared. Plug all that in your calculator, and you should get 128 pi, because we can't forget the pi, feet cubed per minute. Okay, so if you have pi in your answer, I would prefer it if you did not give it to me as an approximate form. I would prefer it if you left pi as your answer, okay, in terms of your answer. It'll just be easier for me to grade and easier for me to check. Kind of like how with the derivatives, I don't want you guys to simplify your derivatives unless it's a multiple choice question, okay? Same thing here. All right, this last one, then we'll take a quick break. It says the radius is decreasing at 4 feet per minute and the height is increasing at 2 feet per minute. Find the rate of change of the surface area of a cylinder when the height is 10 and the radius is 8, okay?
Pi r squared h.
So surface area formula that we need, your surface area is equal to both of the circles on top and bottom. So that's 2 circles with a radius, or not a radius, but an area of pi r squared. So 2 pi r squared is the radius, or sorry, the area of the top and the bottom circles. And then plus, if I unraveled a cylinder, what would it look like? A rectangle. So take the area of that rectangle would be the circumference, which is 2 pi r, times your height in between the 2 circles, so times h. That is your formula for surface area of a cylinder. Now, again, if you don't remember that, that is okay. It will either be given to you or you can ask and I will tell you what it is, okay? If on your homework you're not sure what the formulas are, look them up. You guys know how to Google surface area formula of a cylinder, yes? If you don't, learn that skill because you're going to need to Google a lot when you get to college. Google, Google, Google. Answer your questions, okay? So, we're given the radius, so dr dt is equal to 4 feet per minute. Oh, but it's decreasing, so what should that be in front of it? A negative. And then my height, so dh dt, increasing at 2 feet per minute. And I want to find the rate of change of surface area. So I want to find, I'm just going to label it dSA over dt, our surface area. Or you could just say dA over dt. So we're finding that when the height is 10 and the radius is 8 feet. Okay. So before I plug in anything, I have to take the derivative. So go ahead right now and try taking the derivative of this function. I will tell you you'll have to do the product rule for the second term of r times h, but 2 pi is just a number. So treat it like a number, okay? But leave your answer in terms of pi. So take the derivative, see if you can't get that answer, and then I'll go over it here in a few minutes. All right, I'm taking the derivative with respect to time.
Wait, why is it DA now?
Oh, sorry, I meant DSA. There we go. So I've got 4 pi r dr dt
What? Unless we both did wrong.
plus
No, we definitely both did wrong.
2 pi. And then now I'm going to take the derivative of r times h. So I'm going to do the first one down times the derivative of the second plus the second one down times the derivative of the first. And now I just got to plug in all the information that I know. So our surface area is changing at a rate of 4 pi times 8 feet times negative 4 feet per minute plus 2 pi times my radius, which is 8 feet, times dh dt, which is 2, oh, technically there's that parentheses there. Okay, so times 2 feet per minute plus my height, which is 10, times negative 4 feet per minute. So after I plugged all that stuff in, now we just have to simplify it, okay? And again, I'm leaving my answer in terms of pi. So I'm first going to take 4 times 8 times negative 4. If I multiply all three of those together, I get what? What's negative 128? Perfect. Negative 128 pi. And my units would be feet squared per minute. Oops. And then the second one here, I multiply all these things together. Let's do 8 times 2 plus 10 times negative 40. So I get plus 2 pi times negative 24 feet squared per minute. And then I can go ahead and combine these two things together. So my surface area is changing at a rate of, yes, negative 176 pi feet squared per minute. Okay, so we need to first draw a picture. The ones on your homework, you have not been given a picture. You have to draw a picture, okay? So you'll have 9 problems. You have to draw your pictures for them before you can actually solve. So this says we've got a camera mounted 3,000 feet from the space shuttle landing, or the launching space. The camera needs to pivot as the shuttle is launching and needs to keep the shuttle in focus. If the shuttle is rising vertically at 800 feet per second, when it is 4,000 feet high, how fast is the camera to shuttle distance changing? So I'm going to draw a little picture here. Okay. I've got, this is my space shuttle.
The line.
Yep. I'm not an artist. The space launch zone. Launch. The space launching zone, or the space launching pad. Okay. Then it says the camera is 3,000 feet from this position. So 3,000 feet from this. How would I draw that on my picture?
A dotted line.
But where?
In the middle. On the bottom.
Yeah, like on the bottom, like over here, right? So like this distance, that's not really a straight line. Here, let's try that again. So that distance right there is going to be 3,000 feet. Okay, so this right here is where my camera is. That little circle right there. So as we can see here, we have a triangle. Yes?
Wait, okay, so is this?
So it's saying when the shuttle is 4,000 feet high. Okay, so it's being launched over here, but then we're looking at when this distance is all the way up at 4,000, right? But we know that this rocket here is rising at 800 feet per second. So let's just like assign some variables here. Let's just say that this is y on this side, okay? So our dy dx, not dx, dt, sorry. dy dt is equal to 800 feet per second. Okay. So we're not going to solve letter A. I'll come back and show you that in a video. I want to solve letter B. Okay, letter B is actually the same problem. However, it's asking us how fast the elevation or the angle of elevation of the camera is changing. So we're looking at this angle. Whoa, that was way large. We're looking at this angle down below. Looking up, what is that angle changing at? Like, what is the rate of that angle changing? Okay, so I'm still going to use dy dx or dy dt is equal to 800 feet. But how do I know, like, how do I relate two side lengths and an angle? What do I have to use? Trigonometry, right? Specifically in this case, we're going to have to use tangent, right? So tangent of our angle, this is like our formula that we're using, our equation. So tangent of theta is equal to, when our y value is, oh, sorry, we can't plug in our values yet. We got to have y divided by our adjacent side length there is 3,000. Okay, so that is my equation. And now I have to find the derivative of this. Okay, that's my equation here that we're starting with. Now, the derivative of this, derivative of tangent is secant squared. Secant squared of theta is equal to derivative of y divided by 3,000. Do I really need to do the quotient rule? No, because it's just really like 1 over 3,000 times y, right? So this would be 1 over 3,000 times dy dt, right? And now what are the units for 3,000? Feet. Okay. Now, the left-hand side is where the trig comes into play. A little breakdown of secant. Secant of theta is the same as 1 over cosine of theta, right? So secant squared of theta is the same as 1 over cosine squared of theta. Yes? If I were to evaluate specifically for the triangle that we're given, I would have 1 over cosine. Cosine would be adjacent over hypotenuse. So I've got 3,000 feet over my hypotenuse. I'd have to find that. But my hypotenuse, I've got 3,000, 4,000. So my hypotenuse is 5,000. Okay, so I'd have 1 over 5,000. No, wait, sorry. Adjacent first. So 3,000 over 5,000. These are both squared. And then I can go ahead and simplify that, right? I can multiply it by the reciprocal here. So it'd actually be 5,000 squared divided by 3,000 squared. Which, yes, we could simplify this to be what? Yeah, 25 over 9 or 5 squared over 3 squared, right? So 25 over 9. So now I just evaluated secant squared of theta is equal to 25 over 9 in the case of our problem, okay? So now I can come back to my equation here, okay? And I'm going to plug in the stuff that I know. My secant squared of theta is 25 over 9. 25 divided by 9 is equal to 1 over 3,000 feet times dy dt. dy dt I know. My dy dt was 800, right? So 800 feet per second. Yes. Oh, and I forgot. When I evaluate this over here on the left-hand side, is this 25 over 9 in radians or degrees? It is in radians. So this 25 over 9 should also have a radians next to it. So 25 ninths rad. Okay, and then I can just go ahead and simplify this. So I take, oh wait, where's my, oh, I forgot my variable, you guys. I'm slacking. Okay, when I take the derivative, sorry, pause back here really quick. When I take the derivative of tangent, I have secant squared of theta, but then I also have d theta dt. I forgot to take the derivative there. My bad. I'm so sorry. So I know that secant squared of theta is now, what did I just have? 25 ninths. So 25 ninths radians. Okay, times d theta dt. And now I can go ahead, simplify this stuff out, and I'm going to end up with d theta dt is equal to 0.096. And let's think about the units here. If we're talking about how an angle is changing in relation to time, what should my units be?
Degrees.
Or were you looking at radians, right? So radians per second. Okay.